Hi boys and girls, I want to talk a little bit about how to interpret a redox table. So I've written here some reactions, some reduction reactions as they would appear in a redox table. Most of the reactions, as you can see, are missing because the tables are much more complex than what I'm showing, but I've just picked out a few reactions. So when you look at a redox table, anything to the left of the arrow is called an oxidizing agent. It's an oxidizing agent because it itself is reduced. It's gaining electrons, so in gaining electrons, it's causing something else to lose its electrons, so it's referred to as an oxidizing agent. Substances on this side, the right side of the arrow, are all reducing agents. They cause other substances to be reduced, and in so doing, they're oxidized. They let go of their electrons, somebody else captures them. So in letting go of their electrons, they're causing somebody else to gain them. So they are reducing agents. So never mix up the oxidizing agent side with the reducing agent side. You want to always focus on one side at a time. So I want to look at a question like this. We're going to throw in tin 2 permanganate with cobalt 2 iodide under acidic conditions. And these are solutions. So if they're solutions, we know we have water. Acidic conditions means we have H+. These are ionic compounds, so they split up into their corresponding ions. Tin 2 is Sn2+. The permanganate ion is MnO4-1. Here we have cobalt +2. This is not diatomic iodine. It's simply 2 iodide ions, I- ions, 2 of them. We need 2 of them because if each carries a -1 charge, we would need 2 to counterbalance the +2 on cobalt. Diatomic iodine is iodine bonded to itself. It's bonded to itself because it has 7 valence electrons, and the 8th is sharing with the other. It's getting an 8th by sharing with the other iodide. So that makes it stable. It does not have a charge. This is different. This is I-. It gets the 8th electron by stealing it from cobalt. So you would have this scenario here. That would be the Lewis symbol for iodide. We just simply have 2 of those ions. So totally different than I2. So don't get confused by that there. Okay, so if we want to decide what reaction could happen here and who would be the oxidizer, who would be the reducer, what we should do first is look at the entities and find them on my chart. So I've labeled them here. So tin is down here, I put a square around it. MnO4 over here, a little square around it as well. Cobalt is on that side, I circled it in red. Iodide is on that side, I circled it in red. There's the hydrogen, I put a box around it. I forgot to include the reaction for water, but we actually don't need it in the end. It's not going to be relevant. But you should find the water as well. Okay, so I'm going to focus on everybody who's on this side, which is MnO4, hydrogen ion, and tin 2. So they're all oxidizing agents because they're to the left of the arrow. The strongest oxidizing agent is the one that's going to react first. It's the one at the top of the list. It's MnO4-. So the reaction will occur between MnO4- and the strongest reducing agent. So to find the strongest reducing agent, you look to this side of the table. And the strongest reducing agent is the one closest to the bottom. That's the most likely one to experience oxidation. So cobalt 2 is above iodide, so the strongest one is closer to the bottom, so the reaction will occur between MnO4-1 and iodide. And you simply copy these reactions out. You would flip this one, and then you make sure that the electrons lost equal the electrons gained, and you add them up to get the net reaction. And then you could add their potentials. When you flip a reaction, you flip the sign of the potential, and then you can add them. Or simply you can just find the potential by using the formula E cell is equal to E cathode reduction minus anode, where oxidation. So this one, this negative sign will flip the sign of where the oxidation is happening, and it accomplishes the same thing as you flipping the sign yourself and then adding values. Okay, so one more time, just be very careful that when you're looking at the substances here that you're given, that you choose reactions you're actually allowed to use because you have all entities. So when I chose MnO4-, you have to be careful because it's reacting with 8 protons here. If you don't have acidic conditions, that would not be a viable reaction. That could not happen because you don't have the right conditions for it. So you'd have to move on and choose something else. So make sure that when you're selecting your reaction, you pick the highest oxidizing agent, the lowest reducing agent which would be the strongest. Highest here would be the strongest. Lowest on this side is the strongest. And those are the two that are going to react to make the reaction, in the redox reaction, pardon me. You can't choose a reaction that has something in it that is actually not part of what's in your solution. The only one you're allowed to choose is one that is reacting with something in your solution or not reacting with anything at all, and say just involving electrons. Say for example here with tin, it's just tin is gaining electrons to form, tin 2 is gaining electrons to form tin metal there. So there's no other reactant there, so that's totally fine. If this did not have acidic conditions, as I said, not a reaction that you could use. Okay, so hopefully that answers some of your questions. Thank you.